Alright, hell yeah, we got dynamics. This is part 7. So what we're doing is differentiation. And on this one, we're going to differentiate with respect to time. So we have this actuator. I don't know what it's called. But anyway, we got this, this disc, and it spins like this. And this follower, I guess that's what they called, travels down and then travels back up. Okay, so in this one, we're just going to get to it. So we draw this circle. And here is the point of rotation. Here's the center of the circle. And so we get this triangle to form. And then here's the actuator at A. And hell yeah, so this angle is theta. You know what I mean? So when theta is 0, it's going to be in this vertical position. And what we want to do is, well, let's take a step back. Because how do we get what we want? We want the velocity of this of A, so the velocity of the follower. And so what we need to do is find the length of this. I typically call this, or I have been calling this y. So if we find the height of y as a function of theta, well then we can take that equation of y and then differentiate it with respect to time. So we can take dy dt, and then we can get the acceleration of that length. So hell yeah, and the acceleration of that length, how much that length is changing, will be the velocity of A. Cool. So now how do we, and then typically we get this position in terms of theta. We've done that before. How do we get it in terms of just the variable time? Well, we need to use this equation. We need to say that the theta as a function of time is, the theta initial. In this case, that's just going to be 0. At time is equal to 0, I'm just going to say, hey, it's going to be in the vertical, and then as it sweeps out to like 60 degrees, you know what I mean, a certain amount of time passed. And so we say it's plus omega t. And this is going to be and then how do we get that? Because that's where I got, and I was just like, we need to kind of take a step back, because even in that, you know what I mean, you can't just guess that. You need to kind of figure out why, kind of what's the rhyme and reason. So we're going to take a car. Now, I guess the comparison is an angle change is no different than like a distance, like how far you went as a distance. Or I should say the angle is similar to the distance. The actual change in angle, in omega is radians per second. That's the same thing as velocity. So we're going to take a car, and we're just going to have a car traveling down kind of a path, and it's going to go 30 meters per second. And so what we can do is we can say, hey, velocity is the change in position, change in time. That's the definition of velocity. And so we can just, put this in for v. So we can say dx dt is equal to 30, and then we can separate the variable. We can take this dt and put it up here, and then we'll get this. We can integrate it, and we'll get a equation for position. That's going to be 30. This goes to 30t, but we're going to have to add a constant. And then what this says is at position 0, or no, what it says is at time 0. If we go 30 times 0 seconds, at time 0, well, we're at position 0, so it's 0 is equal to 30 times 0 plus a constant. So this constant has to be 0 for this to match both sides. Okay, hell yeah. So this is the equation for position given velocity. So now you can kind of see the similarity. If we have radians per second times time, that's going to give us the angle. Just like if we have velocity in meters per second times time, that gives us our position. Now this is the case if we don't have any acceleration. In this case, we're just going at a constant speed. Acceleration is 0. If we have a cliff jumper and we're jumping into water, we start with an acceleration of 9.8. We say that's going to be dv dt. We separate variables and integrate. We get 9.8t plus c1. Now, if we're saying that we have initial velocity of 0, this goes to just 0. But if we have to keep it, if we do have some sort of initial velocity, when we integrate again, when we say velocity is dx dt, separate variables, hell yeah, we're going to get this, this is going to, we're going to go t to the 1 plus 1 is 2, so t to the 2 divided by 1 plus 1 is 2, so we're going to get t to the 2 divided by 2. That's why this becomes 4.9 t squared. This will just pop a t. If we do have an initial velocity, you'll have that initial velocity times t plus a new constant. And then when you throw in time is equal to 0, well, is position 0? Sure, you can say position 0 up here. And so that's just going to be x is 4.9 t squared. Anyway, so and this would be the same if we do have angular, if we have a change in angle, if we angular acceleration is some sort of constant, and you know, a positive number, or I mean just a positive or negative, but a number, not just 0, then we would do that same structure here. We would say that angular acceleration is d omega dt, and then we would separate variables. We would say, and then we would integrate to get the equation for omega. It would be whatever that number is, t, and then we would integrate again, d theta dt, and we would say that theta is that angular acceleration, t squared, 1/2 the angular acceleration, t squared, plus whatever initial angular acceleration, angular velocity we have times t. So you still have that omega t, and then you still have an initial angle. So that kind of spells it out, where, hey, I knew that my angular acceleration for this problem is 0, because what we have is, I mean, basically for this one, it's, you know, just pretend like it's on a motor. That motor's spinning at a constant speed. It's hella fast, but it is constant. All right, hell yeah. So other than that, other than figuring out how, you know, all these omegas, I don't have any papers from prior, but yeah. So anywhere where, well, I guess, yeah, like right here where we have this theta. I'm sorry if I said omega. Wherever we have theta, that's where we're going to put that omega t, because that's what we have for our equation. Theta as a function of time is omega t, and so, and then we're going to do this one kind of the 100% method. So here I'm going to, sure, like the easiest thing to do is say, hey, I know this hypotenuse. This eccentricity is a constant. It's just the distance from the point of rotation to the center of the circle. And then also this radius doesn't change. So this doesn't change, this doesn't change. Cool. But these values do. This length, and this length right there all change depending on what angle this is. If we know this is the hypotenuse, this is the angle, sun is shining, so this is E. This hypotenuse sine theta, this is E cosine theta, this is the radius, this is the larger number of the hypotenuse, so these components, this is the sun is shining on the sinin. If this is the angle, make some sun rays, and hell yeah, this is the sine component. And so we have r sine phi and then r sine cosine. But we want to do it kind of the legit way. We want this in terms of theta, not in terms of phi. And so we already know that this length of this triangle is just E sine theta, so sweet. So since we know that, we can figure out what this length is. That's just going to be r squared minus this E sine theta squared square root that. Using Pythagorean's theorem, kind of backwards. We know the hypotenuse. So the hypotenuse squared minus this side squared, square root that. That's going to give us, you know, this value in here. And so we just do it right here. We just bring the square to the, we square the E, we square sine theta. And then so all we do is just everywhere where we see theta, throw in this omega t. And then we have it as a function of time. So you could even say this angle is omega t. This is E sine omega t. and see how we're doing that. So we have e cosine omega t, but these two lengths, these are the most important ones for our differentiation. We're saying if we know this length and we know how it changes as a function of time, if we take that length y and then say dy dt, that literally is the velocity of this this length. You know what I mean? This length will change. This length will now have velocity, like the change in length divided by time. So that's going to be the velocity at a. All right, sweet. So what we do is we take the equation for y at any given, and you would say angle, but now we're saying any given time. So now we're gonna, if you take this plus this, that's what we have up here, the square root of all that plus this. This is this length as a function of time. There is no theta in here. And everything else is a constant. R, E, those are constants. Sweet. So now we can just differentiate. We can take dy dt. You know what I mean? So we take dy dt, and then we take the derivative of this entire thing, dt. And we can differentiate with respect to t. Now, you might think you don't need to use chain rule, but hell yeah, we do chain rule all over the place, because even this square root, we're going to be like, hey, that's u to the 1/2. This is going to be cosine of u. And so if we're going to differentiate these, we're going to differentiate with respect to u. So we're going to go d of cosine u du, but then we're going to use the chain rule. We're going to go du dt. So that's kind of the last thing we're going to do. So then if we have, this was u, but then we see that it has a t in there, so then we'll differentiate with, so if we differentiate this little thing, this u, with respect to t, that's just going to give us a w. And hell yeah, so then it's really similar to what we've done before. You pop out this w, hey, that's reminiscent of that theta naught. You know what I mean? So we're going to still have that kind of theta naught term. But yeah, let's walk through. So even though, hell yeah, that's totally the chain rule, but sure, as long as we have a function of time and we're differentiating with time, like, you know what I mean, we don't have to, kind of technically, we don't have to use the chain rule. We don't have to differentiate with respect to theta and then have a d theta dt component. But it all plays out in the wash, so it is kind of interesting to see the similarities. Alright, so here's my process, or I mean this is just the process for differentiating. I just set it up where if I have square roots, I just bracket them in and just say like, hey, that's like that to the 0.5. So then what I do is I bring down that 0.5, hell yeah, and then I bracket everything in here, and then I take the power, minus 1, so it goes to negative 0.05. But see how that's so much better than actually like taking it downstairs? Keep everything on the same level. Sweet, so we did that process. But, that's just the same thing here. If we take the derivative of u to the 1/2, that's going to be 1/2 u to the negative 1/2 du dt. So we need to take the derivative with respect to time of the inside. And we get more u substitutions, because inside we're going to find that we have a sine squared theta. And we're gonna treat that like u squared. So we do have a constant. So let's see where we're at. So we already did this part. Half came down. This went to negative 0.5. Now we're multiplying it by the differentiate, the du dt. We need to take the differential with respect to time of the inside. This is going to be 0 because it's a constant. Negative 1 and then e squared. I'm just going to say this is a negative 1, but negative 1 and e squared are constants, so we're just going to put those right here. And now we can work on that sine squared. And again, I'm going to treat it like it's sine omega t all squared. So bring down the 2, and then I'm just going to multiply that by sine omega t to the 1 power. I'm just not showing that 1 power. But, I mean, I could right now. You know what I mean? So that's kind of what it would look like. This was sine squared. We bring down the squared, and then it's going to be sine omega t to the 1. We're still not done because it's a u substitution. We got to take the derivative of what's inside. And we got to do that twice, you know what I mean? Because the derivative of what's inside is a sine of omega t. We're just going to treat it like a sine of u, you know what I mean? Or just focus on the sine part. So the derivative of sine is going to be cosine. So we're going to have cosine of whatever was inside, but now we need to take the derivative of whatever was inside with respect to time. And sweet, there is a t there. So that's just going to be omega. Hell yeah. This one's going to be a little bit simpler. We're going to have a constant out front. A derivative of cosine. Cosine is a function that goes like this. It has a slope of 0 when when the angle is 0. So what function when you throw in 0? Well, I'm just going to say sine of 0 is 0. So this is going to be a sine, but look at this. The slope is always negative. So the derivative of cosine is going to be negative sine. That's how I remember, and hell yeah, that's how you should remember. Anyway, so we have e negative 1 sine of the angle. But it's still a kind of a u substitution, you know what I mean? We're basically just saying this is e cosine to the, simple unit of like x or u or whatever. And so we're saying e negative 1 sine of omega t. Well, it's a u substitution. You have to put whatever was in there, but then differentiate also with respect to what is in there with respect to time. So, hell yeah. So that's where you get that omega. And booyah. So... yeah, we're basically there. I just kind of went one step further because sometimes maybe you want to actually clean this up so it looks like that. So we had the 1/2 and the 2. I got rid of those. We do have this negative 1, so I just pulled that right there. And this is like a square root, but it's downstairs. So we have the square root of all that. And then, these already canceled. So then we have the sine omega t, cosine omega t times omega. And then this one, not much changed on this one. Hell yeah. And when we throw this into our calculator, that's kind of the last thing we're going to do. We got negative alpha e squared sine omega alpha t. And I have all these in my calculator. Oh, damn it. We need to figure out what the time is. That's the only thing, because we need to know the velocity at 60 degrees. And the problem statement says this thing's rolling. This thing's rolling at 100 revolutions per minute. So we wrote real small, but well, we have that equation for omega t. You know what I mean? So we have omega. That's going to be 60 degrees, or whatever it is in radians. So that's where we convert to radians. So that degrees in radians, it's about 1 radian, 1.04 radians, is equal to, yeah, now I know this, 1.047. After doing this problem, because the angular speed was 100, well, it was 104.7 radians per second. So it's going to be 6,000 degrees a second. So that's kind of fascinating. But anyway, so we have 1 radian is equal to 104 radians per second times t. And we just solve for t. So that's going to be the time at 1 radian if we have a speed of 104 radians per second, which we do. And so that's what I did, the factor label method here. We converted revolutions per minute. All right, hell yeah, sorry about that. We're back. And so, yeah, revolutions per minute divide by 60, you get revolutions per second. Multiplied by 2 pi radians, you get radians per second. And hell yeah, so 104.7 radians per second. This is 1 radian per second. So we take this 1 divided by 104, and we get this 0.01 seconds. So that's in my calculator is alpha t. The radius on this is 100 millimeters. This distance for eccentricity, that's 60 millimeters. Omega, which, yeah, we do have, that's going to be 104.7 radians per second. Okay, hell yeah. So now we can just go for it. The velocity at time of 0.01 seconds, which is 60 degrees, because this thing is going 17 revolutions per second. So it only takes 100th of a second to get 60 degrees. Pretty wild. Okay. So we have negative alpha E squared sine omega t cosine omega t times omega. I'm just going to go multiplied by alpha r squared, minus alpha e squared sine alpha theta squared. Whoa. We've got to do this omega t. Alpha omega alpha t. Okay, nice. Alright, parentheses. This is to the negative 0.5. See, it's all upstairs in my calculator. Alright, minus alpha e sine theta. It's not theta, so it's omega t, yeah. Whoa. Alright, omega t. And then omega. Alright, booyah. So we get a velocity of negative 7,352 millimeters per second, which is a velocity of negative 7.35 meters per second. This is the last video I'm going to do on this problem. So this is part 7. We've done it 100 different ways. Pretty sweet. And hell yeah. So we're just going to look up the answer just to make sure we got it as 16.96 or something. What is this one? I don't even know. 16.96. Okay, yeah, 7.3 meters per second. I mean 7.35. So that's what we got. Hell yeah. I'm pretty satisfied with this, you know what I mean? All the different methods of differentiation, kind of the different ways to do it. It seems like there's a bunch of different ways to kind of tackle a problem with differentiation. And for the most part, I did mention in one of them, I didn't make a full video on it, but I differentiated each of these separately, or I made an equation where these got separated. So then I couldn't get them back together, and that was the only time where I was just like, nah, that ain't going to work. But for the most part, you could have some, some really complicated way to get there. It's just going to take you more steps. But because differentiation is a like, hey, we're doing, like to get from point A to point B, there has to be a continuous path. It's kind of Newtonian mechanics. You can't just superposition yourself, from one point to another. Everything has to be a logical, this for that. Like, hey, you were here, and it's got to be a smooth, continuous thing. So that's kind of the interesting thing that I'm kind of learning about differentiation in the realm of classical mechanics. So it's pretty cool. All right, thanks for joining me on this one, and that's a video.